Welcome to AI and Machine Learning Deep Dives. Today we're taking a deep dive into support vector machines, SVMs. My mission for us today really is to unpack why these algorithms, despite all the newer techniques popping up, remain so incredibly powerful. They're great for making these precise distinctions, even in really messy data syncs spam filters, or even like critical medical diagnoses. Let's dig into their genius.
Absolutely. So SVMs, they're a type of supervised machine learning algorithm, which just means, they learn from labeled examples, like teaching a system to tell apples from oranges based on examples you've already labeled. The core task with SVMs is finding the best possible way to separate different groups of data points.
Okay.
So at its heart, an SVM identifies what we call a hyperplane. Think of it as just a decision boundary, but potentially in many dimensions. It gives you that clear dividing line.
Right, so if I'm picturing this in just 2 dimensions, that hyperplane is basically a line, right? And maybe a flat plane in 3 dimensions.
Oh.
But like, what makes one particular boundary the best one? That's the bit I really want to get. How does it choose?
Yeah, that's a great question, and it's really central to why SVMs work so well. The goal isn't just any boundary, it's to maximize the margin.
Your margin.
Exactly. The margin is the distance, the gap between that decision boundary and the data points closest to it from each class. And those specific points, the closest ones, we call them support vectors.
Okay, because it sort of hold up the boundary.
Precisely. They literally support or define where that boundary has to be. And by maximizing this margin, making that gap as wide as possible, we get a classification that's more robust, more confident. It's less likely to be thrown off by, small variations.
Okay, that makes a lot of sense for neat, tidy data where you can draw a clear line. Real-world data, it's often messy, isn't it? What happens if it's not, well, linearly separable? Like those classic examples of points in concentric circles. No straight line's going to separate those neatly.
Right, exactly. And that's where the famous kernel trick comes into play. It's actually quite ingenious. What it lets us do is take that data, the stuff that isn't separable with a straight line or flat plane in its original space.
Yeah.
And we implicitly sort of transform it. We map it into a much higher dimensional space. And the clever part is, in that higher space, it often becomes linearly separable. It's like finding a new angle where the problem simplifies.
Whoa, okay, so let me see if I follow this. You're saying we conceptually lift these points into another dimension,
Yeah.
or maybe a third dimension for those circles, and then up there we can just slice between them with a simple flat plane. But how do we do that without the calculations getting completely out of hand? Higher dimensions sound computationally, expensive.
That's exactly the trick part. We don't actually need to do all those heavy, explicit calculations in that super high dimensional space. We use something called a kernel function. And this function cleverly calculates the similarity or relationship between pairs of points as if they had been transformed.
So it's like a shortcut.
It's a very effective shortcut. It gives us the benefit of the high-dimensional separation without the massive computational cost. A really common one you'll see is the radial basis function kernel, the RBF kernel. It uses a parameter, gamma.
Gamma, right. What does that control?
Think of gamma as controlling how far the influence of a single training example reaches.
A small gamma means points far apart can still influence each other, leading to a smoother, kind of broader boundary, more general.
A large gamma, on the other hand, means only points very close to each other matter. This can lead to a much more complex, wiggly boundary that fits the training data really closely.
But that sounds like it could be risky, right? Fitting too closely.
Exactly. That's the danger of overfitting. A very large gamma can make the model highly sensitive to the specific training points, maybe too sensitive, so it doesn't generalize well to new data.
Okay, so the kernel trick handles the nonlinearity. Brilliant. But what about just messy data? Real-world stuff often has outliers, or maybe some points from different classes just overlap a bit. Perfect separation might not even be possible or desirable.
Yeah, that's a super common scenario, and SVMs have a way to handle that too. It's called soft margin classification. Basically, this technique allows the model to make a few mistakes on the training data. It introduces some tolerance for misclassifications.
So it doesn't have to be absolutely perfect.
Right. It makes the model more robust to outliers, those weird points far away from the rest, and also works when the classes inherently overlap somewhat. We control this tolerance level with another parameter, usually called C. It's a regularization parameter.
Okay, C. How does that work? Is it like the gamma thing?
Sort of, but it controls a different trade-off. Think of C as like A budget for errors, or maybe how strictly you enforce the margin. A large C value means you penalize misclassifications heavily. You're telling the model, stick to the margin, keep errors minimal. This can lead to a narrower margin, a harder margin that might be less flexible.
And a small c.
A smaller C is more forgiving. It allows more points to be misclassified or fall within the margin in exchange for potentially achieving a wider, smoother margin overall. This often leads to better generalization on unseen data because you're not fitting every single point perfectly. It's this constant balancing act,
So
balancing margin width against training errors.
that makes sense. You need
Yeah.
that flexibility. So, okay, SVMs are great for classification, putting things into boxes, even when it's messy. But can they do more? What about predicting, say, continuous values, like house prices or stock prices, regression tasks?
Absolutely. That's where support vector regression, or SVR, comes in. It uses the same core ideas, hyperplanes, margins, kernels, but the goal is different. Instead of finding a boundary to separate classes, SVR tries to find a hyperplane that best fits the data points within a certain margin.
So it's trying to get as many points inside the margin as possible.
Exactly. It aims to fit a function to the data such that the errors for most points fall within a specified tolerance within that margin or tube around the function. And it has advantages over, say, traditional linear regression. It's often more robust to outliers, and thanks to the kernel trick again, it can model complex nonlinear relationships really effectively.
Wow, okay, so classification, regression, handling messy data, nonlinearity. It sounds incredibly versatile.
Yeah.
Given all that flexibility, where are SVMs really making a difference today? What are some key applications?
Oh, they're used all over the place, genuinely. Image classification is a big one. Think recognizing handwritten digits like on postal codes or in more complex tasks like face detection systems. They're also really, really good for text classification.
Like spam filtering?
Spam filtering is a classic example, yeah. But also things like sentiment analysis, figuring out if a review is positive or negative, or categorizing documents. And beyond that, you see them in bioinformatics, for instance, classifying proteins or genes. In finance, for things like credit scoring or predicting market trends. Even in medical diagnosis, helping to identify diseases based on patient data. Their ability to handle high-dimensional data and find optimal boundaries makes them still very relevant.
Really impressive how enduring they are. A testament to the core ideas.
Definitely. The concepts of maximizing the margin in the kernel trick are just fundamentally powerful.
That's all for now, folks. Please like, share, and subscribe for more like this.